Hello, and welcome to this video demo of the TGEN tool within the ePOP experience. TGEN is a tool within ePOP to generate and size transmissions for inclusion in your ePOP studies. To assess the various system-level powertrain attributes accurately, we need to know certain information about the transmission, such as the mass and efficiency. TGEN enables you to create this data for multiple transmission concepts using just a few inputs. You could use this capability to identify the optimal transmission architecture for a potential vehicle. Or as a system integrator, you may use it to enable vehicle level calculations prior to having detailed transmission data available. For this demonstration, we're looking to create a transmission for a small EV to match an existing 150 kilowatt motor. In this tool, we have the option to use a variety of typical transmission layouts that you may expect in electrified applications. Single speed, multi-speed, two-stage and three-stage, with other arrangements also in development to be added soon. So as an example, let me go to one of the standard layouts, which is widely used in electric vehicles. Single speed two-stage layout. Now the single speed two-stage can be characterized. You can set targets for your design. Our motor has a peak torque 240 Newton meters and a maximum speed of 16,000 RPM. So we enter that in here. For the transmission, we can look at a range of concepts. Let's start from a ratio of 10 to 1, go up in steps of 0.5 to 11 to 1. And if I click generate ratios, then we get three different concepts with a 10.5 to 1 ratio in the middle, 10 at the bottom, 11 at the top. If I change my parameters and I want a wider selection of ratios, say 8 to 1, all the way up to 14 to 1. And I want them more frequent in resolution, say 0.1 increments. And in this case, we've generated 60 concepts of very many different ratios across that range. Now at this point, I've only generated ratios, so there are no masses, dimensions, etc. yet. That's in the next step. Let's go back to a lower number, maybe 10 different concepts, to make sure we're still spanning a broad range of concepts. Let's look at a range from 9 to 1 up to 13.5 to 1 with 0.5 steps. Here we have our 10 ratios chosen. We can then adjust the macro geometry of the gears, the assumptions that are used in the sizing. I'm going to leave most of this as default, but I'm going to make the output wheel dip in the oil slightly just so we can see some churning losses. And then we can adjust the bearings that are being assumed on each shaft. For the purpose of demonstration, I'm going to change my output shaft to be on taper roller bearings with just a little bit of preload. Now, if I'm happy with my ratios, I can hit concept generation and wait perhaps a couple of minutes. What happens now is the software will generate all those target concepts with gears size for the torque they're being asked to transmit, bearing size for the load they need to react. This conceptual sizing is being developed with the assistance of drive system design, drawing on over 15 years of experience in powertrain design and analysis. From this geometry of the components can be approximated the masses and the inertia is calculated. All the geometry is macro level, so we know the number of teeth, the rough geometry of the teeth, at a macro level, not micro, and bearing diameters. Using this data, the losses are then calculated. We understand where the bearings are. We understand the working geometry of the gear meshes. So the loads and speeds at each location can be calculated along with the associated losses using ISO standard calculations. This is the same as you may get from software such as Master or Romax. However, TGEN enables you to get this data from multiple transmission concepts at once without having to create a detailed model for each one. The output of this process is a data file that is directly usable in the main ePOP environment to perform simulations. Now, our generation is complete. 10 concepts have been generated with different ratios. Each of them has a 2D map, a 2D layout, beg your pardon. And we can change to this particular example is our 9:1 ratio. And if we scroll across, we can select the different ratios, and we can see that the layout is different. So for let's look at our lowest ratio. We should have a 9:1. And you can see that it's the center distances approximately from the layout. We've got maybe 75 millimeters on the first stage, a bit more on the second stage, but overall the kind of input to output center distance is about 190 millimeters. For the other ratio extreme, 13.5, you can see the center distances are larger, as you would expect, with the input to output being more in the region of 235 millimeters. Now, all these concepts have the shafts in a single plane. In reality, they would probably be wrapped around to bring the input and output closer together, so they form a triangle. But for the purposes of such a study, we're interested in the resulting mass and efficiency. So such an simplification will have minimal impact. And then finally, and most importantly, we have the losses that are calculated for the various components in the transmission. So we have losses for each of the gear meshes, each of the pairs of bearings on each shaft. And as I specified the output gear to be slightly dipped in oil, we also have some churning losses. And we can select all these together, and we get a loss map for the entire transmission. And we can view that either as losses or as efficiency. This is the efficiency map of the transmission concept, and this is exactly what is used by ePOP for the system analysis. So if we return to ePOP, and in our pre-processing environment, we hit reinitialize just to pick up the transmission data that we've generated. Then we can create a new study, more EV. Select our architecture type, which in this case is going to be a BEV single motor 2-wheel drive. And if we hit pre-process, then we can see that the software has picked up that there is a combination with our pre-existing motor and the transmission ratios that we've generated that we can now run a study on. Once that study runs, we'll then be able to look at the system level powertrain results. So our study has run. We just need to load our data file. we can select from here. Then we can look at the results of that study in detail. No, we can't because it's not working. Oh. Start that section again. Once our study has run, we can load our results file. Once loaded, we can view all our system level results. So we have our 10 different ratio concepts with our connected to our example motor. You can see that they're consuming a different amount of energy across the cycle that we specified. And if we select one of these, we can look at some of the details for that particular specification. So the one I've selected here is the 11.5 ratio. And then we can view the residency points from the cycle across the efficiency map of the entire powertrain system. And in the top right here, if we select transmission, we'll see the familiar transmission efficiency map that we viewed just now in ePOP and TGEN, now being used in ePOP for the full system level results. Further information on the sizing calculations carried out by TGEN and the way it creates the geometry, calculation of the loads and losses, etc., are also available under the help system within the main menu of TGEN, along with example calculations used to validate the software. Thank you.